Index. Introduction. Emissions from an electric vehicle. The point at which an electric vehicle offsets its emissions with its use. Polestar 3 case. Lithium extraction. Environmental implications of lithium extraction. The unknown emissions of electric vehicles. Materials used in the electric vehicle. Energy used in the electric vehicle. Battery manufacturing. Polluting emissions from internal combustion engines. NOx polluting emissions. CO polluting emissions. CO2 polluting emissions. HC polluting emissions. Polluting emissions particles. SOx polluting emissions. Technologies to reduce polluting emissions. Place where polluting emissions occur. Involvement in fleet management. Subscribe to the Fleet Management channel. Your subscription is a great support to continue making new videos. Subscribe. 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 Emissions from an electric vehicle. What emits more CO2, an electric car or a car with an internal combustion engine? With the need to stop climate change, the world has begun to measure the carbon footprint of everything we consume. From a commercial airplane flight, clothing, to cars, everything has a carbon footprint. It is a recurring question and one that several studies have tried to answer, some being more controversial than others. Still, there seems to be some consensus that electric vehicles are the best compromise to make transportation as green as possible. A study carried out by the vehicle manufacturer Volvo and recently published provides a new perspective to this question with a complicated answer. And Volvo's position to carry out this type of study is unique. Volvo can compare identical internal combustion engine, plug-in hybrid and fully electric models, all built on the same platform and in the same factory. Volvo has taken advantage of the study carried out on the carbon footprint of its electric Volvo XC40 Recharge to compare the carbon footprint of the entire life cycle of each type of gasoline XC40 from the raw materials and production processes necessary for its manufacture, through fueling from well to wheel and driving over a useful life of 200,000 kilometers until disposal at the end. Study carried out on the carbon footprint by Volvo. The quantified pollutant emissions of the study are the following. 1. Extraction and processing of raw materials. It contemplates the polluting emissions generated by the extraction and processing of vehicle raw materials such as steel, aluminum, lithium, cobalt, rare earths, etc. 2. Manufacturing of the vehicle. It contemplates the polluting emissions generated by the painting, assembly, etc. processes of the vehicle. Body painting is an energy-intensive process. 3. Use of the vehicle. It contemplates the emissions generated by the energy used in the vehicle. If it comes from renewable energy, there are no polluting emissions. 4. Vehicle recycling. It considers the emissions generated by the recycling and dismantling of the vehicle. 5. Transportation. It includes the emissions generated by the transportation between the factories of the materials to the assembly factory, from this to the dealership, and the transportation to the recycling center. And what has Volvo discovered? Manufacturing an electric XC40 involves 70% more CO2 emissions than manufacturing an XC40 with an internal combustion engine, since both cars are built on the same platform and share many of their parts. If we talk only about materials and components, leaving aside battery cells, the manufacturing of an XC40 Recharge causes almost 30% more greenhouse gas emissions in the XC40 Recharge compared to the XC40 gasoline, mainly due to the higher use of materials in the XC40 Recharge and the highest proportion of aluminum. Manufacturing an electric car emits more CO2 than manufacturing a gasoline car. This means that these electric cars arrive at the dealership having already emitted more CO2 compared to the gasoline version. Now, we must also take into account the use of the car. Once they begin to circulate, the electric car will hardly involve CO2 emissions, while the gasoline car will continue to emit CO2 in greater proportions. While the carbon footprint of electric vehicles is being drastically reduced, that of gasoline is adding more and more CO2 to the equation. The main reasons why producing an electric car has a much larger carbon footprint than manufacturing a gasoline or diesel car are well known. Most greenhouse gases are generated in the mining and processing of the various raw materials that make up the car and the battery, such as lithium, steel, or aluminum. Green NCAP claims that it pollutes less than one with a combustion engine if the entire life cycle of each one is taken into account, around 30% less.
Learn about our fleet management consulting and training services. Reduce costs and optimize fleet management activities. We electrify your fleet of vehicles. We carry out the electrification plan until its implementation, known as
the point at which an electric vehicle offsets its emissions with its use. The point at which the increasing CO2 footprint of the internal combustion engine car exceeds that of the electric vehicle and continues to grow depends on where the electricity to charge the electric vehicle is obtained. Volvo has published 3 different figures according to the global energy mix, in which fossil fuels abound, the mix planned in the European Union plus the United Kingdom, and finally, a scenario in which the energy is completely renewable, wind type specifically. According to the global energy mix over a life cycle of 200,000 kilometers, the carbon footprint of the electric XC40 is lower than that of the internal combustion XC40 after 146,000 kilometers. According to the European Union 28 energy mix, it is after 84,000 kilometers that the carbon footprint of the XC40 begins to be lower than that of the gasoline XC40. And in the supposed case of being able to recharge the XC40's battery with 100% wind energy, the balance point would be reached at just 47,000 kilometers. Tons of CO2 equivalent. The total polluting emissions for a use of 200,000 kilometers are as follows. The internal combustion XC40 has the most total emissions with 58 tons of CO2 equivalent, followed by the electric 45 tons of CO2 equivalent, and in first position is the wind-powered electric XC40 with 27 tons of CO2 equivalent. Implications in fleet management. The most important conclusion is that to achieve the maximum reduction in CO2 equivalent emissions, the electric vehicle with renewable energy must be used for around 200,000 kilometers. It must be considered that if the battery has to be changed to continue using the vehicle, the total pollutant emissions increase and the balance point would be higher. It may happen that we purchase an electric vehicle and do not reach the necessary kilometers from the equilibrium point, and it pollutes more than its gasoline counterpart. In passenger cars and SUVs in a fleet of vehicles, it is recommended to have a renewal policy of 4 or 5 years and at most 150,000 kilometers, to have new vehicles because they have the latest technologies in safety, batteries regarding the environment, consumption, etc. Renting contracts for passenger cars or SUVs for this type of vehicle are usually 15,000 kilometers and 4 or 5 years. So in the best of cases, renewable energy would only offset a very low figure of CO2 emissions. And with the mix of the European Union, the emissions would be higher than its gasoline counterpart. Currently, it is advisable to purchase electric vehicles on rent due to their high depreciation, but to achieve a considerable reduction in polluting emissions by using the electric vehicle with renewable energy, it is necessary to travel about 180,000 to 200,000 kilometers, which is the average run by fleets with this type of vehicles are more than 8 years old, so you must acquire the vehicle as ownership because there are no leasing companies that make contracts of more than 5 years on this type of vehicle. The ideal scenario would be to make a rental contract for 4 or 5 years and travel 200,000 kilometers before changing the battery. Currently, an electric vehicle that is more than 8-10 years old and has 200,000 kilometers in which the battery must be changed has a very low residual value. WLTP cycle and not EPA, rare earth mining and other criticisms of the Volvo study. Like all studies, this one can also be criticized. It can be argued, for example, that in reality the equilibrium point is obtained much earlier than what the study indicates. To calculate consumption, both electricity and gasoline, Volvo has used data from the WLTP cycle, Using the more realistic US EPA cycle, the break-even point would arrive sooner. True, but in this study it is not so much about knowing when it occurs, but simply knowing if it occurs or not, and if so, in what proportion. The question is whether, despite the brutal impact on CO2 of manufacturing an electric vehicle, it can be compensated for later. Clearly, even with some data in favor of the gasoline car, the WLTP cycle is lax in that sense. It is possible to offset the carbon footprint with some ease. On the other hand, it is worth remembering that yes, Volvo has taken into account the carbon footprint of E5 gasoline from the well to the wheel. Of course, variations in this electric balance point are possible depending on its energy mix. Charging that car in France, where more than 70% of energy is nuclear, or Norway, a champion of renewable energy despite being an oil producer, is not the same as in countries where energy is generated by thermal power plants and especially of coal. Burning coal to produce energy is much worse than burning natural gas. Specifically, burning coal emits twice as much CO2 as burning natural gas. Thus, depending on the energy mix from fossil sources, the point at which the carbon footprint of the electric car begins to be lower than that of gasoline or diesel can be delayed. We also cannot overlook the useful life of the battery. Volvo assumes a useful life for its model of 200,000 kilometers. In a gasoline or diesel car it is a fairly common mileage, but in an electric car it is not common yet. The unknown is how long a battery will last before being changed. Let us remember that most manufacturers guarantee at least 70% of the original capacity of their batteries up to 160,000 kilometers. If a new battery is needed before those 200,000 kilometers, the car's carbon footprint would increase significantly again. Although it is true, on the other hand, that the turning point at which an electric vehicle has compensated for its initial CO2 footprint occurs between 70,000 and 110,000 kilometers, depending on the recharging energy mix. On the other hand, Volvo's carbon footprint study focuses on, pardon the redundancy, the carbon footprint on the CO2 emitted. Greenhouse gases are a problem, but it is not the only threat to our ecosystem. The mining of lithium and rare earths necessary for the manufacture of battery cells for electric cars is not exactly an ecological activity, although it is rarely mentioned. The extraction of these rare earths and other necessary minerals requires enormous amounts of water, and these mines are usually, to make matters worse, located in arid areas. Polestar 3 case. The manufacture of a Polestar 3 long-range dual motor, a 4.90-meter long SUV with a 111 kilowatt-hour battery, is equivalent to emitting 24.7 tons of CO2 equivalent. In the case of the Polestar 3, the brand assures that it has made progress in reducing the carbon footprint of the manufacture of the Polestar 3 thanks to the use of renewable energy in the production of the batteries, saving 1.7 tons of CO2, as well as in the car aluminum production, saving 6.8 tons of CO2. If it had not been done, the carbon footprint of the Polestar 3 would be 33 tons of CO2 equivalent and not 24 tons of CO2 equivalent. Despite being a much larger car than the Polestar 2, the brand's entry-level model, the Polestar 3 emits only 1.7 tons of CO2 equivalent more than the 2024 Polestar 2. However, the Polestar 3, like any other electric car, arrives at the dealership having already emitted more CO2 than an equivalent gasoline car. But that's only part of the picture. You must also take into account the use of the car. So how much CO2 does a Polestar 3 emit in total? The total carbon footprint of a Polestar 3 from its manufacturing to the end of its useful life after 200,000 kilometers ranges between 28.5 and 44.5 tons of CO2 equivalent, depending on the energy mix used to charge it during its life. Useful. The lowest figure corresponds to the use of 100% renewable electricity of the wind type, while the highest figure corresponds to the global energy mix, in which the burning of coal and natural gas abounds. In the same scenario, a gasoline Volvo XC40 will emit 58 tons of CO2 equivalent over its entire useful life, of 200,000 kilometers. That is to say, even in the worst-case scenario, an imposing Polestar 3 will emit less CO2 than a much smaller and less powerful gasoline car such as the Volvo XC40. Lithium extraction. With the need to reduce CO2 emissions via the massive use of lithium-ion batteries, we could be creating another problem, just as harmful or more so. Lithium is not found in a free state in nature. It is dispersed in rocks, clay, and brine, a mixture of water and salts. Its extraction is slow, consumes a lot of energy, and requires large quantities of water, an increasingly scarce resource. To extract lithium from rocks, as is particularly the case in Australia, which is the world's largest producer, and in China, it is first necessary to crush them. After this, water is added to form a paste that is placed in a tank where the air allows the lithium to be separated from the rock. After filtration, the obtained lithium powder is further refined. To do this, it is heated to a temperature of up to 1000 degrees. Chemicals and water are then added before another filtration. The process, which takes between 1 and 2 months, is expensive due to its high energy consumption. In addition, the use of water and chemicals makes it not very respectful and friendly to the environment. In the salt deserts of Argentina, Bolivia, and Chile, home to the world's largest lithium deposits, the metal is found in brine, a mixture of water and salts. To extract it, you have to pump the brine from the depths and then place it in giant buckets so that the water evaporates. Once the salts have solidified, they are moved to the bottom of the pools after 12, 14, or 16 months, depending on weather conditions. The aqueous solution obtained is transferred to another plant, from which, after filtration and the addition of chemicals, lithium carbonate and in some cases hydroxide will emerge. Although less expensive, this extraction method is also slow and above all consumes large amounts of water. Lithium is essential for electric car batteries, and the demand in the next decade will be enormous. Lithium is present in small quantities in the anodes and cathodes of the cells that make up the battery, and an electric car battery has on average about 160 grams of metallic lithium per kilowatt hour. Manufacturers do not usually reveal that information. Lithium is found in fragile ecosystems. It is true that there are large deposits in Chile, in the Atacama Desert, and in the Uyuni Salt Flat in Bolivia, as well as in the province of Salta, Argentina, which is already the third largest producer in the world. In these cases, extraction is quite simple and a priori with low impact in an already arid area, and yet it takes about 2 million liters of water to produce 1 ton of lithium. This enormous water consumption not only affects the surrounding ecosystems, but also has a huge impact on local farmers. According to the Environment and Natural Resources Foundation, Lithium Extraction in Argentina 2019, which interviewed the 10 communities that live near 2 salt mines, Sales de Jujuy and Minera XR, the mine's detractors say they are concerned about the long-term impact term of lithium in the environment, starting with the lowering of the water table, stating that livestock in the region have already begun to die. The consequences of mining on the ecosystem have also been seen in other regions of the world. In May 2016, hundreds of protesters threw dead fish into the streets of Tagong, a city on the eastern edge of the Tibetan Plateau. They had been pulled from the waters of the Liki River, where a toxic chemical leak from the Ganzhizhou Rongda lithium mine had wreaked havoc on the local ecosystem, and it could go further. Research conducted in Nevada, where lithium is also mined, found impacts on fish up to 150 miles downstream from a lithium processing operation. Now the entire industry relies on the new deposits inside the Arctic Circle. Russian state mining company Rosatom, which also mines lithium for nuclear weapons, is studying the possibility of opening a mine on the Kola Peninsula by 2030. This site, called Kolmazero, is located within the Arctic Circle. Furthermore, also in the Arctic Circle, the Swedish company Arctic Minerals AB has reserved other exploitable land. According to Jari Natunen, a mining expert at the Finnish Association for Nature Conservation, mining in the Arctic would be catastrophic. It says that the difficult extraction of lithium from the frozen earth would generate 50,000 tons of toxic waste for 1,000 tons of lithium produced. The Arctic Circle has already borne much of the cost of materials for electric vehicles, as the Norilsk nickel mine, the most polluted place in the world, provides the material that is replacing the problematic cobalt and has only generated a new problem. Environmental implications of lithium extraction. There are 4 environmental implications of starting a lithium mining industry. The viability of any lithium extraction project will depend on an adequate response to each of them. 1. Responsible use of water. Lithium extraction often involves intensive use of water in the mining and extraction processes, which can have an impact on local water resources. It is important to implement efficient and sustainable water management practices and ensure that water supplies for local communities, agriculture, or other essential uses are not compromised. 2. The correct management of waste and chemicals must be taken into account. An industry of this type will generate waste and chemical emissions that must be managed appropriately. It is essential to carry out exhaustive environmental impact studies and apply mitigation measures to protect the biodiversity of the affected areas. 3. Energy use and carbon emissions. While lithium is a key component in the transition to cleaner energy, the extraction and processing of the mineral requires a considerable amount of energy, so it will be advisable to look for renewable energy sources that minimize the carbon footprint of the entire company supply chain. 4. Take into account the participation and consultation of local communities. Lithium extraction can have a significant impact on local communities, both in terms of employment and changes to their environment. For this reason, it is essential to involve communities in the decision-making process, provide clear and transparent information on possible impacts, and ensure that adequate risk and benefit assessments are carried out before starting any project. The unknown emissions of electric vehicles. The dilemma of batteries and PFAS. PFAS are a collection of more than 4,700 widely used synthetic chemical compounds that accumulate over time in humans and the environment. Lithium-ion batteries found in mobile phones and electric cars also contain these PFAS. Research finds a new subclass of chemical contaminants, PFAS, used in lithium-ion batteries. It is becoming an increasing source of air and water pollution. The team of researchers found that PFAS, specifically bis-perfluoroalkyl sulfonamides, exhibit similar environmental persistence and ecotoxicity to older well-known compounds such as perfluorooctanoic acid. The dilemma posed by the manufacture, disposal, and recycling of these chemical agents in a lithium battery forces us to develop recycling technologies and solutions that combat the climate crisis without releasing highly persistent pollutants. PFAS and their drawbacks. Researchers sampled air, water, snow, soil, and sediment near manufacturing plants in Minnesota, Kentucky, Belgium, and France, finding high concentrations of bisphaceae. Furthermore, atmospheric emissions of bisphaceae can facilitate its long-distance transport, also affecting areas far from manufacturing sites. Analysis of municipal landfills in the southeastern U.S. suggests that these compounds may enter the environment through the disposal of products, including lithium-ion batteries. Although the toxicity of bisphaceae has not been studied in humans, other PFAS are linked to cancer, infertility, and other serious health harms. Treatability testing indicated that bisphaceae does not break down during oxidation, but its concentrations in water could be reduced using granular activated carbon and ion exchange, methods already used to remove PFAS from drinking water. Treatments developed to remove PFOA and PFOS may also work for bisphaceae, and their use is likely to increase as treatment facilities are upgraded to meet EPA's new maximum contaminant levels for PFAS. Materials used in the electric vehicle. The most used materials in the manufacture of electric vehicles are aluminum, steel, and battery materials. The European Federation of Transport and Environment has revealed an analysis highlighting the importance of the use of green steel in the automotive industry. Steel produced using green hydrogen and electric arc furnaces or from scrap metal has the potential to reduce CO2 emissions. The analysis reveals that adopting 40% ecological steel would only increase the sales price of an electric vehicle by €57 in 2030. Furthermore, achieving 100% green steel in 2040 would have a negligible additional cost of only €8 compared to conventional steel due to CO2 pricing and the reduction of production costs of green steel. Energy used in the electric vehicle. How the energy used in the electric vehicle has been generated is essential. To achieve the maximum reduction in CO2 equivalent emissions, the electric vehicle must be used with renewable energy such as wind, geothermal, hydroelectric, tidal, solar, or wave energy. It is necessary to know the origin of the energy that is being used to recharge electric vehicles. It is best to use energy generated by renewable energies to calculate the equivalent CO2 emissions of the vehicle fleet. You can use energy generated in our facilities by solar panels or windmills, or contract renewable energy with an energy company, or do both at the same time. Energy mix of the countries. In some countries, they do not have a supply of all the energy generated by renewable energies, so polluting emissions have been generated in the generation of energy in the use of electric vehicles. There is an open source interactive map that allows any interested citizen of the world to understand the energy mix of each country or the climate impact of the electricity consumed in real time, to understand what is behind the simple gesture of turning on the light or recharging the battery of your electric car. Electricity Maps is a small startup from Denmark and France that wants to publicize the climate impact of the electricity consumed around the world based on data made public by electricity grid operators, official agencies, and others. With them, they calculate the amount of greenhouse gases emitted for each unit of electricity consumed. The greener the country, the more climate-friendly the electricity consumption. In Europe, there are not too many countries painted green. Norway, Iceland, and Sweden are represented as those that produce the least CO2 emissions with their electricity, followed by Finland and France. In the case of the latter, we can see how today there is only 28% renewable in their energy mix, and yet they generate almost clean electricity thanks to nuclear power. In fact, over the past 10 years, France was Europe's leading electricity exporter thanks to a large nuclear fleet that produces low-cost, low-carbon electricity. Spain, which in 2023 has broken a historical record in renewable energy generation, is painted yellow and pollutes 3 times more when it comes to producing electricity than France, since natural gas continues to be the most used, most expensive, and most polluting source. Germany is one of the countries with the most installed solar energy, but due to coal, it has emissions of 350 grams of CO2 equivalent kilowatt hour. Poland has a very high figure of 600 grams of CO2 equivalent kilowatt hour for coal. If we were to use this generation mix, the electric vehicle would not make any sense because it would have more CO2 equivalent emissions than its gasoline counterpart. Although Poland has an energy mix of 600 grams of CO2 equivalent kilowatt hour, you can surely contract 100% renewable energy with an energy company. The energy mix of the United States is very varied depending on the state. Battery manufacturing. Currently, to analyze the environmental impact of batteries, the amount of electricity necessary to manufacture them is taken into account. But the European Union wants to take into account the origin of the electricity used in these batteries. It is not the same in China, the world's largest producer of batteries, as it is in South Korea or Spain. In Spain, there is an energy mix with a large proportion of renewables, which helps to have very low polluting electricity. The idea is to introduce, starting in 2027, the national energy mix factor in the calculations of the carbon footprint of the production of a battery and the electric vehicle. The goal is to reduce the carbon footprint of vehicles and reward countries that have cleaner electricity production. According to a new analysis by the European Federation of Transport and Environment, a battery manufactured in China generates about 120 kilos of CO2 equivalent per kilowatt hour of capacity, while manufacturing it in Europe with the current energy mix would lower that figure to 76 kilos of CO2 equivalent per kilowatt hour. With predominantly renewable generation, emissions would drop by 62% to about 45 kilos of CO2 equivalent per kilowatt hour. Polluting emissions from internal combustion engines. Every combustion process has an associated problem of polluting emissions. The amounts of polluting emissions are highly variable, depending on the type of engine, degree of load, mixture dosage, or combustion chamber temperature. They are mainly due to chemical imbalance due to freezing of equilibrium reactions when gases cool. Others are products of combustion failures, partial oxidation of the fuel, pyrolysis and dehydrogenation particles. Pollutants are classified depending on their origin. Primary are those emitted directly from the source. Secondary, they are formed in the atmosphere by reactions between the primary ones. Both are harmful to health and the environment. Polluting emissions from internal combustion engines. The main contaminants of the combustion process in an engine are nitrogen oxides NOx, carbon monoxide CO, carbon dioxide CO2, which contributes to the greenhouse effect, unburned or partially burned hydrocarbons HC, PC particles, sulfur oxides SOx. In vehicles, pollutants are measured using different measures such as the amount of pollutant per distance traveled grams kilometers, grams megajoule, percent volume, parts per million or billion, or milligrams grams second. Polluting emissions from internal combustion engines. The four main effects of polluting emissions on the troposphere are alteration of atmospheric properties and precipitation, damage to vegetation, deterioration of materials, potential increase in diseases and mortality in humans, unburned or partially burned hydrocarbons and nitrogen oxides together with sunlight photochemically generate tropospheric ozone and peroxyacetyl nitrates, producing a yellow-brownish cloud that is irritating to the eyes and respiratory tract, known as photochemical smog, which usually occurs in polluted environments, hot climates, with a lot of sun, and at midday. NOx polluting emissions. The term nitrogen oxide refers to various chemical compounds formed by the combination of oxygen and nitrogen, such as NO2, N2O2, N2O4, N2O, N2O3, N2O5, and NO3. NOx is the generic way of designating the nitrogen oxides emitted by the engine, mainly NO and NO2. NOx is due to the oxidation of atmospheric nitrogen N2, the main component of air, at high temperatures with a high oxygen content. In engines, NO is mainly generated, and secondary NO2 is generated due to the conversion of NO to NO2. The amount of NO2 reaches values between 10 and 30% of NOx emissions, having greater potential than NO for the formation of acid rain and photochemical smog. NO is generated in the combustion process by three mechanisms. Thermal, it is the most important at high temperatures, and is produced by the oxidation of nitrogen present in atmospheric air, being the oxidant of combustion. In diesel engines that generally tend to work with lean or close to stoichiometric mixtures, the main reactions that govern the formation of NO are those developed by Zeldovich, and which are used to estimate NO emission. Fenimore's sudden prompt. It is formed in the first phase of combustion, when atmospheric nitrogen reacts with hydrocarbon radicals existing in the air. Intermediate N2O. It is important at low temperatures and in the combustion of lean mixtures. The best known processes are those of Lavoie and Terns. NOx polluting emissions. NOx are one of the main causes of acid rain and producer of photochemical smog. In contact with rainwater, NO2 produces nitrous acid and nitric acid. NO2, reddish-brown in color and with a pungent odor, irritates the lungs and reduces resistance to infectious diseases if the level exceeds 600 milligrams per cubic meter. NO reduces ozone in the stratosphere, facilitating the passage of ultraviolet solar radiation to the Earth's surface. Nitrous oxide has a great impact on the greenhouse effect, which is 296 more effective than CO2, and its great stability in passing through the atmosphere and participating in the destruction of stratospheric ozone, although the concentration in the exhaust gases is very small. CO polluting emissions. The mechanism of CO formation is a fundamental intermediate step in the oxidation of a hydrocarbon. and it is related to the dosage of the mixture. In the diesel engine, it is usually caused by using lean and heterogeneous mixtures. The combustion of a hydrocarbon can be divided into two stages. In the first, or rapid reaction, the molecules are broken to form CO, while in the second, it is the oxidation of CO to CO2. In the atmosphere, CO is oxidized to form CO2. In diesel engines, the formation of CO occurs for two reasons: low loads with high excess air. The lean mixture zones are not capable of supporting rapid combustion because the flame cannot propagate through this zone, and products from pyrolysis and partial oxidation of the fuel such as CO and aldehydes are formed. High loads with low levels of excess air. The rich zones are not able to mix with enough air to produce complete oxidation of the fuel. CO polluting emissions. CO is colorless and odorless. It is lethal in low doses because it combines with hemoglobin in the blood more quickly than oxygen and reduces the ability to carry oxygen. An exposure to 600 parts per million for 3 hours can cause death. Normal street concentrations of 30 mg per cubic meter cause fatigue, headache, vomiting, and drowsiness. CO2 polluting emissions. CO2 is formed by the oxidation of hydrocarbon in the combustion process. CO2 emissions are directly proportional to fuel consumption. In a diesel engine, approximately 2.67 kilograms of CO2 are produced from the tank to the wheel for each liter of fuel, and in a gasoline engine, 2.42 kilograms of CO2 are produced. They depend on two parameters that describe their composition: the hydrogen-carbon ratio and the oxygen-carbon ratio. Fuels with low carbon concentrations such as ethanol, biodiesel, natural gas, etc., they generate less CO2 than diesel. A diesel vehicle with the same characteristics and power has fewer emissions of grams CO2 kilometers than the equivalent gasoline vehicle because it consumes less, although its CO2 emissions value from the tank to the wheel is higher. HC polluting emissions. Unburned HC hydrocarbons are mainly emitted due to incomplete combustion of fuel, and its composition is very heterogeneous. The main reasons are flame extinguishing due to the wall effect or misfiring, insufficient fuel evaporation, short circuit of fresh load, fuel trapped in small volumes, extreme local dosages, fuel composition, direct impacts on health such as irritation of the respiratory system and eyes or carcinogens are not important due to its short life in the atmosphere, but it has a great impact on the formation of photochemical smog. HC polluting emissions. There are two main hydrocarbons emitted. The main hydrocarbon emitted are polycyclic aromatics pH. At least 32 types have been found. They are formed during the incomplete combustion of organic matter. The most common PAHs in engine emissions are naphthalene, phenanthrene, pyrene, chrysene, and fluoranthene, and they are probable carcinogens. The other main hydrocarbon emitted are carbonyl compounds. These compounds are not present in the fuel, but appear in intermediate stages of combustion. The different oxygenated compounds found among hydrocarbons are alcohols, phenols and derivatives, aldehydes and ketones, and carboxylic acids and derivatives. Polluting emissions particles. A particle is any matter present in the exhaust gases that is in a solid or liquid state under ambient conditions. There are two groups of particles. The primaries are formed as a product of the combustion process. Secondary ones, resulting from a process such as sedimentation, evaporation, condensation, growth by collision, etc., which is produced both in the exhaust and in the atmosphere, and which are regulated in the different anti-pollution regulations. Soot is the initial substrate for the particles. There is a relative dosage limit in which it appears. Along the exhaust there is a reduction in gas temperature, and the soot agglomerates are subjected to hydrocarbon adsorption and condensation phenomena, causing the formation of particles. The particles are composed of two fractions separable through a chemical extraction process, of which independently the main component is soot. An insoluble fraction having organic and inorganic compounds called ISF, which is mostly composed of soot along with sulfates, hydrocarbons, ashes, salts, water, and inorganic materials. A soluble organic fraction called SOF, composed of hydrocarbons and other organic compounds from fuel and lubricating oil. polluting emissions particles, PM particulate matter. The danger of particles depending on their size may be different depending on the fuel used. In general, the smallest particles are the most dangerous for the following reasons. Greater likelihood of inhalation, penetrating the lungs and bloodstream. They have a longer residence time in the atmosphere. The residence time of particles of 0.10 microns is 1 week, causing a decrease in atmospheric visibility and contributing to the fouling of buildings. They have a greater specific surface area, which facilitates the adsorption of potentially carcinogenic organic compounds. There are particles emitted by brake pads, tires, or asphalt. That regulation is beginning to be studied to limit its emission. Emissions Analytics has carried out tests using a medium-sized sedan with new tires inflated to the manufacturer's recommended pressure. After measurements, they discovered that the car was emitting 5.8 grams of particles per kilometer due to the tires and brakes, a figure more than 1,000 times higher than the limit established for particles in exhaust gases, which cannot exceed 4.5 milligrams per kilometer. The problem could be even worse if the tires were underinflated or the road surface was rougher and rougher, wears more rubber. The study has focused on PM 2.5 and PM 10 particles, tiny particles whose diameter is less than 2.5 and 10 micron respectively. These types of particles are very dangerous due to their high potential damage to health. The wear generated by the tires and the dust that comes out of the brakes when they rub against the pads and discs are the causes of these emissions. SOx polluting emissions. Sulfur S is found in liquid fuels, either in the form of organic or inorganic compounds. Due to the danger of sulfur oxides, SOx, legislation has been legislated to reduce their content in fuels. The main major compound formed by the combustion of sulfur S is sulfur dioxide SO2, and to a lesser extent SO3 if the mixture is lean. If the mixture is rich, HS, H2S and COS are formed. Sulfur dioxide is an irritating colorless gas with a penetrating odor, perceptible at different levels. Its density is twice that of air, it is not a flammable or explosive gas, and it is very stable. It is very soluble in water, and in contact with it, it converts into sulfuric acid, being responsible for acid rain. SOx polluting emissions. SO2 can produce the following adverse effects, even at great distances from the emitting source. Health as irritation and inflammation of the respiratory system, lung conditions and insufficiencies, alteration of protein metabolism, headache or anxiety, biodiversity, soils and aquatic and forest ecosystems, causing damage to vegetation, degradation of chlorophyll, reduction of photosynthesis and the consequent loss of species, buildings through acidification processes. Well, once emitted, it reacts with water vapor and other elements present in the atmosphere so that its oxidation in the air gives rise to the formation of sulfuric acid. In addition, it also acts as a precursor for the formation of ammonium sulfate, which increases the levels of PM10 and PM2.5 with serious consequences on health as well. Technologies to reduce polluting emissions. CO2 emission cannot be reduced and or decreased. For each liter of fuel, 2.67 kg of CO2 are produced in a diesel engine and 2.42 kg of CO2 in a gasoline engine from the tank to the wheel. For the rest of the emissions, a combination of technologies are currently used to reduce their values depending on the substance and what is wanted to be obtained at the end of the exhaust line. The technologies most used in engines to reduce polluting emissions are catalysts, the particle filter, the EGR valve, the SCR combined with the AdBlue additive. The problem of polluting emissions in diesel engines occurs at specific times, such as engine warm-up, strong acceleration and high load circulation, and this is where action must be taken to have low polluting emissions. During the rest of the time in which the different exhaust gas after treatment systems operate optimally, the NOx emissions of a diesel are so low that they can be compared to a gasoline engine. Exhaust emissions after treatment systems are installed along the exhaust line to destroy substances before emitting them into the atmosphere, and they can operate with different principles such as avoiding certain chemical reactions at low temperatures, oxidation and reduction, provoke or accelerate chemical oxidation reactions of HC or soot, or the accumulation by physical or chemical means of substances. The installation of after-treatment systems affects the mixture formation and combustion system, place where polluting emissions occur. Environmental impact of energy generation with fossil fuels. It must be emphasized that there are studies quantifying deaths and illnesses caused by energy generation with fossil fuels. Burning coal generates harmful dust particles that can be transported long distances from where they were generated at the coal-fired power plant, crossing borders and countries far from where they were emitted. Citizens who do not live nearby can breathe these particles and suffer serious consequences for their health. The 2013 Dark Cloud Over Europe report analyzes the health impacts of burning coal and highlights that coal plants are obsolete and are responsible for 18% of the European Union's total greenhouse gases. This report warns of the serious impacts on the health of Europeans of the emission of gases from thermal power plants. Some of the most notable data: of the 280 coal-fired power plants operating in Europe, 257 are responsible for 22,900 premature deaths, 11,800 new cases of chronic bronchitis, and 21,000 hospital admissions, 538,000 asthma attacks in children, as well as 6.6 million lost workdays in 2013. About 83% of premature deaths were caused by PM2.5 suspended particles. Most of these particles are not generated directly in coal plants, but are generated in the atmosphere from SO2 and NO2 that are emitted in the chimneys of the plants. European and national plants cause 1,170 premature deaths in Spain, comparable to the 1,128 deaths in traffic accidents in the same reference year, 2013. The 5 countries that cause the most deaths outside and within their territory are Poland 5,830 premature deaths, Germany 4,350, the United Kingdom 2,870, Romania 2,170, and Bulgaria 1,570. Spain is the 6th country responsible for premature deaths caused by coal plants, with a total of 1,530 in 2013, of which 840 occur in Spain. The place where polluting emissions occur has more or less environmental impact. The ideal is the use of renewable energy in the electric vehicle, but if it is generated with fossil fuels, it has an environmental impact. Power generating plants that use coal or natural gas are mostly in rural areas, where polluting emissions are dispersed more into the air and have a smaller impact than if they were in a city where they are more concentrated and where a larger population lives. CO2 emissions. CO2 emissions are responsible for the greenhouse effect and climate change, and have the same impact on the environment regardless of where they occur. Emissions of NOx, COHC, etc. They have a greater impact in urban environments than in rural ones, because they are concentrated and manifest as a kind of grayish cloud visible from a certain distance, reducing air quality, causing the appearance of respiratory diseases, cancer, etc. in a larger population. The advantage of the electric vehicle. And this is one of the advantages of the electric vehicle compared to the internal combustion engine, which does not emit NOx, CO, HC, etc. in urban environments that cause respiratory diseases. Implication in fleet management. The advantages and disadvantages of the electric vehicle with respect to polluting emissions are the following. 1. The advantages are: it emits less CO2 than its fossil fuel counterpart above the break-even point. They do not emit NOx, CO, HC, etc. in urban environments that cause respiratory diseases and other diseases harmful to health. 2. The disadvantages are: it emits more CO2 than its fossil fuel counterpart below the break-even point. The environmental impact of mining battery materials such as lithium, cobalt, rare earths, etc. it is very high. If energy is generated with fossil fuels, it emits polluting emissions. The fleet's polluting emissions must be quantified. It is necessary to know the polluting emissions generated by fleet vehicles. Currently, electric vehicle emissions can be quantified from well to wheel. There are different international standards to do so. but the emissions generated from the extraction of lithium, steel, etc., up to the recycling of the vehicle, they must also be considered as belonging to the vehicle and the fleet. Currently, there is no data to carry out this measurement, except for the study published by Volvo, but we must know that these emissions exist. The European Union wants all this data to be public starting in 2027, and that is when all polluting emissions from electric vehicles can be calculated. 100% renewable energy. In order to reduce polluting emissions as much as possible, renewable energy must be used. It is important to contract with an energy company to purchase renewable energy. If energy from fossil fuels is used, the reduction in polluting emissions will be lower, or may even pollute more than the equivalent internal combustion vehicle, in addition to increasing the balance point. There is a balance point of kilometers to be traveled, in which the electric vehicle pollutes less than its internal combustion counterpart. This balance point is lower if we use renewable energy than with energy generated with fossil fuels. The electric vehicle can pollute more than an internal combustion vehicle. If the necessary kilometers are not traveled to reach the balance point, in addition to the impact on the environment of the mining of lithium, cobalt, rare earths, etc., the electric vehicle must be used for a high number of kilometers. To achieve a significant reduction in emissions, the electric vehicle must be used for a high number of kilometers, in the Volvo study up to 200,000 kilometers, which is when the battery is supposed to be changed. Normally, this type of SUV vehicle is available for more than 8 years, and it is not likely that the vehicle can be acquired through renting, so it would have to be acquired as property. The electric vehicle with this high mileage, and if the battery has to be changed, has zero residual value. If we keep the vehicle and change the battery, the total emissions and the balance point increase. Change in renewal policy. It is recommended to have a renewal policy to have new vehicles 4 or 5 years or no more than 150,000 kilometers. When using the electric vehicle for more than 8-10 years or more than 200,000 kilometers to achieve the maximum reduction in polluting emissions, the renewal policy completely changes. The new renewal policy is to travel the maximum number of kilometers without changing the battery, so the average age of the fleet will be very high. From my experience, from a certain age on vehicles of this type, which is usually from 6-7 years, operating costs such as maintenance, breakdowns, accidents, etc., they increase exponentially. Extension of the study to other types of vehicles. The Volvo study has been carried out on SUV vehicles, which are the best sellers on the market. The same study should be carried out on buses, industrial vehicles, sweepers, etc., to find out if the conclusions are the same, which in my opinion would be very similar or the same as the Volvo study, the paradox of the electric vehicle. Nowadays, in general, public opinion and society associate the 100% electric vehicle with zero polluting emissions and tend to ignore the polluting emissions from the extraction and processing of lithium, cobalt, rare earths, the manufacturing and recycling of the vehicle such as has carried out the Volvo study, although there are specialized automotive media that disclose these emissions. The acquisition of electric vehicles and charging infrastructure is more expensive than a fossil fuel fleet, although it can be compensated over time because electric energy is cheaper than fossil fuels. Not only does electrification have an economic cost, it is a very important change in fleet management and a change of mentality in the company towards zero emissions. When the fleet is electrified, the company usually gives a lot of publicity to society, customers, shareholders, directors and employees of the company, etc., and an indicator of the theoretical grams of CO2 kilometer of the fleet is usually calculated using data from the vehicle manufacturer. In a 100% electric vehicle, it is zero emissions. But as developed in the Volvo study, if the break-even point is not reached, the electric vehicle has more total CO2 equivalent emissions than its fossil fuel counterpart, in addition to the environmental impacts of the extraction and processing of the battery materials such as lithium, cobalt, rare earths, etc. And the paradox is that the new electric fleet has even more total polluting emissions than what we had with fossil fuel vehicles, and that the opinion of society, customers, shareholders, managers and employees of the company, etc., is that we have a zero-emission fleet because 100% electric vehicles are used.